Now, one of the key applications of wavelet transforms is in detecting discontinuities, and if you look at this example that we have here on the right, it has done the job for you. We have a sinusoid corrupted with an impulse disturbance. Without any user intervention, it is able to detect the discontinuity as well as the sine wave, whereas in the spectrogram, although we did not discuss this in detail, one has to adjust this width effectively to capture both the impulse and sine wave. You have to do it by trial and error, whereas with wavelets it is very nice, it is very ideally suited for these class of signals, because the impulse is short lived and it is nicely captured by the very high frequency wavelets, and since impulse anyway has a broad spectrum, you do not have to worry about the frequency localization, and a sine wave, at least in this signal, exists for a long period of time, and it is of much lower frequency than any of the frequencies present in impulse, at least the high frequencies. Therefore, it is nicely captured in time very well, but its frequency has been the energy has been smeared in the frequency direction or dimension. Always compare with what you would get with the spectrum, because the Fourier spectrum will give you global features. It is important not to discard that information when you are performing time frequency analysis. One of the first steps in time frequency analysis is to perform a Fourier analysis, get an idea of global features, and then move on to the time frequency analysis. Obviously, when it comes to capturing the frequency content, nothing can beat the Fourier analysis for you, right. Okay. So, we will close this discussion with what is known as with a quick overview of what is known as a discrete wavelet transform. Until now we have talked about continuous wavelet transform. In fact, we had when we gave the definition of the wavelet transform, that is a continuous wavelet transform. What is continuous about it? Do not please attribute that to the continuous nature of the signal. The continuous prefix there has got to do with the continuous with these parameters here, tau and s. When these are continuous valued, then we call them as continuous wavelet transform, pretty much like with other transforms. What we are talking about here is discrete wavelet transform. Again here, discrete does not refer to the signal, but refers to how you choose your tau and s. When I say discrete wavelet transform, it means that both tau and s are now going to take on specific values in a grid, on a grid that I will choose, unlike in a continuous wavelet transform where tau and s are continuous value. So, that is the prime difference. The continuous and discrete have got nothing to do with the signal. In both cases the signal is continuous, right. So, why do we require discrete wavelet transform? The simple answer to that is, if I look at the continuous wavelet transform, I am going to evaluate the transform at every possible value of tau and s. Of course, computationally that is not possible, but what that means is I am going to choose a very fine grid for tau and s to get the picture. Now, when I do that, what happens is, let us say I choose scale equals 1, that is I am looking at the mother wave itself, and I am going to analyze the signal with this mother wave. When I translate with in very fine steps in time, then what happens is there are going to be huge overlaps between the signal segments that I am going to analyze, and that will generate lot of redundant information. Remember, we are going from a one dimensional signal representation to a two dimensional representation, and likewise for scales as well. When I look at two very finely spaced scales, and that is the analysis at two finely spaced scales, again I am going to generate a lot of redundancy. Now, this is not good or useful, desirable in many applications, and the classic application being signal compression, where I would like to represent the signal in as few numbers as possible. So, if you think of such an application, which is of course very widely encountered, then I would like to choose tau and s in such a way, that is this translation and scaling in such a way that ultimately when I am done with the analysis of the signal, these coefficients that I generate by virtue of transform are going to be minimal. That means those are the minimum number of coefficients that I will require to represent the signal in the time frequency plane. And it turns out that if you choose this particular grid for the scaling parameter and the tau translation parameter, then you have what is known as a compact representation in the time frequency plane or in the time scale plane, and particularly when you choose powers of 2, we call this as a dyadic discrete wavelet transform, but normally we leave out the dyadic. It is understood by default discrete wavelet transform always works with dyadic scales, and you should see here that the translation parameter is being chosen proportional to the scale. What this means is, if I choose a particular wavelet of this width, I should shift, I should march ahead proportional to the width. If I choose a wider wavelet, then I should march ahead, my steps of marching should be larger, whereas when I choose a narrow wavelet, the steps that I take in time for translation should be smaller, right, because then I would have covered only a small portion of the signal at each value of the tau, and that is the reason we have the proportionality for tau. That tying together the grids for grid spacing for tau and s makes this a very compact representation, and we will talk about the mathematics of it. How is it guaranteed that these choice of s and tau will generate a compact or what is known as an orthogonal family of basis functions for analyzing a signal? Otherwise, the original transform is always CWT. DWT is not a new transform. It is very popular because of the applications where it is applied, right, signal compression, signal estimation, image analysis and so on. DWT is very popular, but please do not think that DWT is the best technique always. It has its own drawbacks, and CWT is very good, for example, in feature extraction, because it has this redundant information and you can get very nice features, whereas with DWT you may not be able to get the features very well. And there are other drawbacks such as invariance to features. When a feature shifts in signal in time, DWT cannot detect that shift, right. So, there is something called a shift invariant wavelet transform and so on. So, DWT is the answer for many applications, but not for every application, and CWT also has its own place. So, just to give you a feel of how DWT looks like, I have an example for you taken from Mallet's book. That is, the signal itself is taken from Mallet's book, but the figures have been completely regenerated. So, look at the left figure that we have here. On the top, I have what is known as a piecewise polynomial signal. It has features such as discontinuities, very sharp, smooth changes and so on. What is typically done in DWT is, you would actually break this signal into different components at different scales, exactly what the way you would do in CWT. But the terminology is what makes it probably a bit obscure. What you see on the bottom 4 panels here are essentially the coefficients, that is, after you have performed the transform at different scales. The second panel here consists of what is known as approximation coefficients, which is the transform taken of the signal at the coarsest scale. What we mean by coarse is the scale at which the low frequency wavelet exists. And then you have at the bottom, the bottommost, the coefficients taken at the computed at the finest scale, that is the narrowest wavelet that you are using in your analysis. Now, what is the use of these coefficients that I have computed? Notice that the width in time for these coefficients is different at each scale. Sorry, that has got to do again with the choice of tau. We said we will march ahead in time depending on the scale at which I am computing. Now, what do these coefficients give me? They give me the energy contained in the signal at these respective scales. Now, predominantly what you see is a low frequency trend in the signal with occasionally some discontinuities. Whenever there are discontinuities, you will see them reflected in the finer or the high frequency scales, that means values of s less than 1, and the remaining, the most part of the signal lives in the low scale, low frequency domain or high scale, and typically we say trends are approximations, and that is why these are called approximation coefficients. Now, what you see on the right is again the signal on the top, but now I have plotted continuous versions of the signals of the signals components. What are these exactly? Again with the signal on the top, the second one that you see which is denoted here as A3, I have how did I generate this? Well, the simple way to generate this signal here is by zeroing out all the coefficients D1, D2, D3 on the left. So, I am assuming that none of these details should be present in the signal, they were there by some mistake, and I am going to eliminate them, and then I am going to construct the approximation of the signal. So, that is the coarsest approximation of the signal that I am constructing at the scale of my analysis. I can even construct coarser approximations. Then what I have in the remaining 3 on the right hand side here, the uppercase, notice the difference between the notation. I use uppercase for the reconstructed components and lowercase for the coefficients. So, for the D3 also it is the same story. What I do is in constructing this big D3, I will retain only the coefficients in the small D3 and then ignore or zero out the remaining coefficients at the remaining scales. The idea is to reconstruct only that part of the signal, and that is the idea. So, what we are doing is we are reconstructing the signal at individual scales, and if you add up all the blue curves that I have there, you should get the red one. That is a perfect reconstruction property that the discrete wavelet, the wavelets that you use for DWT should satisfy, generally speaking. Now, this is the idea that is used in multi-resolution approximation, that is very common and very effectively used in computer vision and image analysis, where I construct approximations of images at different scales. In fact, if you were to see in many browsers, modern browsers, you would see if you are viewing an image, the image will be displayed to you at different approximations, starting from the coarsest to the finest, right. That is the same idea here. I start again, I have the signal on the top, I have the coarsest approximation that I constructed earlier. Now, what I am going to do is I am going to add this detail big D3 to the approximation and get a better approximation of the signal, and then even a better approximation, and finally the signal itself, because we said when we add up all the broken up components, I should recover the original signal itself. So, this constitutes what is known as a multi-resolution approximation, which is very popular in wavelet theory, right. We will talk about this in detail later on. Now, to conclude, let me tell you that whenever you read literature on wavelet theory, you will find several textbooks written by different people, mathematicians, physicists, engineers, and econometrics people, and so on. Each one takes a different perspective simply because wavelets have such enormous and diverse set of applications. For mathematicians, wavelets are approximating functions. For engineers, wavelets are filters, and for physicists they are time frequency analysis tools. So, depending on the book that you read, it may be heavy in notation or not, and heavy in Greek in symbols and not, and so on. As engineers, what is important is to know how the wavelets are applied rather than really getting bogged down with all the theorems and so on. Therefore, you should try and read material that are presented to you by engineers who are able to give you good perspectives, particularly the filtering and the time frequency analysis perspective. What we shall do in this course sorry, is we will start off with the time frequency perspective and then gradually move on to the filtering perspective. Of course, occasionally we will talk about the approximating part. There is no escape. Whichever perspective you take, you will inevitably be compelled to talk about the other perspectives, but predominantly we will take the time frequency and the filtering perspective of the wavelet theory, because those are the most widely encountered applications in engineering. And you should always remember that all three are equivalent. It is just that the perspective and the utility is different, right. So, with those words, let me close this lecture by, of course, giving you the course outline as well. And the course outline is fairly straightforward in the sense it's already given on the course website for you. The course is divided into several units, or you can call them as modules, and each unit has a set of lectures and I have given the distribution for you. The final unit talks about empirical mode decomposition, but that is more of a special topic. We will not go as much as in detail as we do for the other topics such as short time Fourier transforms, Wigner-Wille and wavelet transforms. The empirical mode decomposition is the most recent one if you look at the historical developments. It as I mentioned, it takes an instantaneous frequency perspective like the Wigner-Wille, whereas the spectrogram and the scaleogram take the regular frequency perspective. Of course, there is this time scale perspective that wavelets take as well. So, let us go through this course together and enjoy the journey. Here are a few reference texts for you that we will follow. Of course, predominantly the material may be borrowed from this, and as I mentioned in the previous lecture, there are going to be notational differences. Please do not get confused between notational differences. What is important is to be consistent with the notation that I use in this course. If you find any errors in the consistency of notation within the course material, please feel free to point them out and to bring them to our attention. The software that we will use is primarily MATLAB, and in this MATLAB platform there have been several open source toolboxes that have been developed, really wonderful toolboxes, and we will use them extensively in this course. Wavelab, the time frequency toolbox, will be used predominantly, and to a certain extent the wavelet coherence toolbox, which is also an open source by Grinstead, Moore and others, and the commercial wavelet toolbox that is supplied by MathWorks to a lesser extent. Okay. So, please be comfortable with MATLAB, make sure that you are familiar with the basic syntax and basic workings of this software. This is a list of references for the lecture that we just went through. Of course, some of these references will run through the entire course, and make sure that you read up the corresponding chapters to get more details on whatever lecture you go through. Okay, so, we will meet in the next lecture. Thank you.